It is called linearity of expectation. The statement will sound very simple to you. Even the proof is very easy. But I can't tell you how important it has been in whatever research I have done and whatever ways it can be applied. I will show you multiple instances where problems become very simple with the help of linearity of expectation. So without further ado, let's talk about it. Suppose I have two random variables, x omega 2r, y omega 2r. We saw that given random variables, we can define functions of it. A very natural function would be x plus y. Again, from the sample space, same sample space to real numbers. How is it defined? We know random variable is a function, so I just give its value. X plus y of w naturally should be xw plus yw. Given such a random variable, the question is, what is expected value of x plus y? You might guess it is e of x plus e of y. And fortunately, this intuition turns out to be correct. We know that this is actually the right answer. We will see a proof of this, but more importantly, we will show implications of this beautiful theorem. The thing to note, I have not assumed anything about the relation between x and y. Whatever way they are related, it doesn't matter, linearity of expectation will hold true. So relation between x and y is not important at all. The proof, as I said, is not difficult. Expected value of x plus y should be summation over all possible values of x and y, probability x is equal to x, y is equal to y, and then the value again. Right? Take some time and convince yourself that this is the formula for expectation. You might think that this is the probability of the random variable x plus y to be equal to x plus y, but that is not correct. Again, at this point, pause the video, notice this fact, and notice that this is the correct definition of expectation. So now we will just simplify it. I will break it into two parts. In one, I will keep x on one side, and in the other summation, I will keep y on one side. Now, since x does not depend on the summation, I can take it out. Y is equal to y. Similarly, for the second term, y comes out and it becomes probability of x equal to x, y equal to y. Now the thing to notice is that this quantity is summation over y, probability of x equal to x, y equal to y. So if I sum it up over all y's, then this will give me the probability of x equal to x. So this is x times probability of x equal to x. Applying the same idea on the other side, it will give me y, probability of y equal to y. And now we can recognize this formula. This is expectation of x and this is expectation of y, giving us the proof of linearity of expectation. Another exercise which you should do is to generalize this. Show that expectation of x1 plus x2 plus xn is expectation of x1 plus expectation of x2 plus expectation of x. So it's a simple exercise. You should be able to show. Most important thing to notice here is no assumption about relationship between x1, x2 and xn. And why I'm emphasizing it again and again is because this gives us the power for linearity of expectation. This tells you that in many situations, this theorem can be applied. First application of this fact can be shown like this. Suppose a student takes 5 courses, let's say probability, discrete structures, operating systems, HSS, and so on. And I know the average marks of students in each of these subjects. So I know that out of 100, people got 35 on average in probability. In discrete structures, they got 40. Operating systems, they got 20. HSS, they got 50 out of 100. And now, if someone asks you, what is the average total marks of students? In this case, average is taken over all students. So I'm interested in summing up marks of each student and divide by total number of students. So linearity expectation shows that this average can be easily calculated using these 5 numbers. It is the sum of these 5 numbers. So again, take it as an exercise and see that this is linearity of expectation. Notice that here we did not need to ask individual marks of each student. I assume that some of you might think that this is very simple. So let's take another example. Let's say you are a fan of chewing gum. I think you might remember when you were young, you had this nice chewing gums. At least they were there in my time, when every chewing gum will give you some kind of a sticker. So we assume that there are n different stickers which come out of chewing gums. So when you buy a chewing gum, you get one sticker. It can be anyone out of these n different stickers. And our task was to collect as many different stickers as possible. So let's ask, how many chewing gums are needed to collect all possible stickers? And we assume that whenever you buy a chewing gum, a sticker comes out with equal probability. So we have stickers 1, 2 up to n. The probability of each of the sticker coming out is 1 by n. So you might realize that this is not a definitive answer, because in the worst case, I can keep getting the same sticker again and again. So then my question would make sense if I say, how many chewing gums in expectation should I buy to collect all possible stickers? That's defining a random variable. This is the number of days to collect all stickers. Okay, and you already know the hint that I have to use linearity of expectation. So pause the video and see if you can calculate this expectation. You will see that it is not an easy task. After collecting I-1 different stickers. So notice that SI is not the number of days to collect the ith numbered sticker. The numbers of the sticker are not important. SI counts the number of days after you have collected I-1 different stickers. They could be 1, 2, up to I-1, they could be n, n-1, n-2, I don't care. But once you have I-1 different stickers, the counting starts and stops as soon as I get the ith different sticker. So make sure that you understand what SI is. Once you define SI like this, then it is easy to see that expectation of T is expectation of S1 plus expectation of S2 up to expectation of Sn. So if I want to find out the expected number of chewing gums to buy, I only have to find out this expectation. So what is expected value of Si? To calculate this, I should find the probability distribution function for this random variable. And that is not very difficult. So probability of Sk being equal to R means I already had k minus 1 different stickers. They keep appearing for first R minus 1 days. So that happens with probability this, and on the rth day I find something different. Okay, so this is the probability of Sk equal to R. Now it's a simple exercise which you should do, which shows that expected value of Sk is n by n minus k minus 1. Using this, you can calculate the expected value of T. Again, pause the video and make sure that you can calculate these values. That would be the end of this lecture. So in today's lecture, we saw conditional expectation and we saw linearity of expectation. We took two examples, but throughout the lecture, we will see numerous applications of linearity of expectation. In the next lecture, we will talk about various probability distributions which frequently appear in probability theory and try to calculate their expectation. Thank you.